Part 2 of Lesson 3.1 on exponential functions is going to be on solving problems involving exponential growth and decay. On Part 1, we talked about exponential growth and decay graphs and kind of analyzed those types of functions. And in this part of the lesson, we're going to be solving problems involving exponential growth and decay. So, first thing, you're going to need to write this down for some notes. This is a compound interest formula. Got a bunch of different letters there. We're going to use that when we talk about money being compounded. All right. A is your amount. P is your principal. Principal is the amount of money that you invest. R is your interest rate. N is how many times a year you compound it. And T is your time. Now, what does it mean to compound? It basically just means that you're going to calculate interest or give money at a certain interest rate n number of times. Okay, so some examples at the bottom. It says Christy invests $300 in an account with a 6% interest rate, making no other deposits or withdrawals. What will Christy's account balance be after 20 years if the interest is compounded 3 different ways: semi-annually, monthly, and daily? So using this formula, here's how we go about finding it. A equals 300 is the principal amount. 1 plus, our interest rate, is always a decimal, so 6% is 0.06, divided by n. Now here, semi-annually means twice a year, so n is 2. Raised to the 2 times, now it says after 20 years. Okay, so we'll have to type that in on your calculator. We'll do that here shortly and find the amount. If we're doing part B monthly, this would be the equation we would set up. The principal 300, 1 plus the interest rate 0.06. Obviously there's 12 months in a year, so now my n value is 12. And we'll calculate that in a moment. And then daily, this is the equation that we would set up. Again, principal is 300, 1 plus the interest rate 0.06 divided by 365 days in a year, and for 20 years. So if you calculate each of those, you're going to get different amounts. Which one do you suppose will give you more money? Well, the correct answer is daily, part C, because you're calculating interest more often, so you're going to make money off of your interest. And so if you look at this chart right here, these are the dollar amounts. If we compound it annually, which is just once a year, we get $962.14 after 20 years. If we had compounded interest semi-annually, this is part A that we just got done doing, which is twice a year, we'd have a little bit more money, $978.61. Quarterly would be 4 times a year. We can see it's even more money. Monthly, that's part B. 12 times a year, we get $993.06. And daily, 365 times a year, which is even a little bit more money. And we could even do it hourly, which would be 8,760 hours in a year, which we earn the most. Another formula to write down is the compound interest formula. Some people like to call this the PERT formula. The amount equals the principal P times the number E, 2.7 approximately, raised to the RT. So, anytime it talks about interest being compounded continuously, which means like all the time, then use this formula. Example 5 lists this, shows this. Suppose Christy finds an account that allow her to invest her $300 at 6% interest rate compounded continuously. If there are no other deposits or withdrawals, what will Christy's account balance be after 20 years? So the equation we would set up, again the principal is 300. Now we use the number E, and then we raise that to the 0.06 times, and we're doing this for 20 years again. Okay, so to type that in your calculator, this is what it would look like. 300. Now E, you have to go second, and then ln. And it gives you E raised to, and it's ready for you to type in your exponent, which in our case is 0.06 times 20. Just like that. And that'll give you the amount that you'd make if interest was compounded continuously. Now we always round to the nearest cent. So you can see this is going to be rounded to $996.04. Pretty straightforward problems. It's just a matter of knowing the formulas. Make sure you get those 2 formulas written down in your notes. 2 more formulas I'd like you to write down. Sometimes we're going to be talking about exponential growth or decay, but it's not going to be with money. And so if it's a growth or decay problem, this is going to be the formula that we use. It's very similar to the compound interest problem. We have an n sub 0, which just stands for your initial amount. We have r, which is your interest rate as a decimal, and t is your time. If we're talking about something growing or decaying continuously, then we use a similar formula to the compound continuous formula. We just have n sub 0, which is your initial amount, versus p for principal. We still have e raised to the kt, where k is the growth rate or the decay rate. All right, so a couple of examples. Get those two formulas written down in your notes. Some examples. Mexico has a population of approximately 110 million people. If Mexico's population continues to grow at this rate, predict the population of Mexico in 10 and 20 years. So we're going to be using this formula right here because it's an exponential growth model. Initial amount. Now, this says 110 million. I'm not going to write all the zeros. I'm just going to remember that this is in terms of a million. Okay, so that's my initial amount. 1 plus my interest rate is 1.42. That's 0.0142, okay, as my interest rate. Now, I wrote this slightly incorrectly. Let me fix that. Big difference between this and the money problems is we don't have to divide by anything. So just go like that, raised to the, we're doing 10 years first, we'll do it again in 20 years. Okay, so if we go to the calculator and type that in, 110, 1 plus 0.0142 raised to the 10th gives us about 126.65 million people. So I'm going to write that down like this. Now if I'm going to round that off, I'm going to round it off and go 3 decimal places, so 657. And if we're going to do the other part of this question after 20 years, we simply would go back to the calculator and enter in the same thing, except for instead of having an exponent of 10, we have to have an exponent of 20. And that would give us 145.836 million. So very similar to our compound interest formula, we just don't have the compounding where you have to divide by 12 if you're compounding monthly. Okay. And same problem now, but if it says, suppose that it's growing at 1.42 continuously, then we use a slightly different formula. We would use this formula right over here if it was growing continuously. So, the equation will look like this: e raised to the 0.0142 times 10. Again, on the calculator to find that. 110. Second ln gives you e raised to the, and then we type in 0.0142 times, it was 10 years, wasn't it? Press enter. We got 126.783. Okay, so that's one of our answers. Comparing that to, this is compounded continuously, comparing that to this previous problem, the answers are pretty close here, aren't they? 126.657 million people versus 126.783 million people. Obviously, we're talking about a lot of people here, but the answers are slightly different. And then to get the second answer here, we have to go back to the calculator and simply type in the same thing, except for having a 20 in the exponent for 20 years instead of 10 years. We get 146.128. 146.128. that's compounded continuously, and comparing that to compounding annually, you get slightly different answers. I shouldn't say compounding, I should say growing. Okay, so here is part 2, one more problem, 31, 32, and 37 through 42. This will be collected on Thursday, in addition to the problems I gave you to start, which was 1 through 20.